The solids shown in Figure 9.14 are pyramids. In Figure 9.14a, point A is non-coplanar with square BCDE. In Figure 9.14b, F is non-coplanar with triangle GHJ. In these pyramids, the non-coplanar point has been joined by drawing line segments to each vertex of the square and to each vertex of the triangle, respectively. Every pyramid has exactly one base. Square BCDE is the base of the first pyramid, and triangle GHJ is the base of the second pyramid. Point A is known as the vertex of the square pyramid. Likewise, point F is the vertex of the triangular pyramid. The pyramid in Figure 9.15 is a pentagonal pyramid. It has vertex K, pentagon LMNPQ for its base, and lateral edges, segments KL, KM, KN, KP, and KQ. Although K is called the vertex of the pyramid, there are actually 6 vertices: K, L, M, N, P, and Q. The sides of the base, segments LM, MN, NP, PQ, and QL, are base edges. All lateral faces of a pyramid are triangles. Triangle KLM is one of the 5 lateral faces of the pentagonal pyramid. Including base LMNPQ, this pyramid has a total of 6 faces. The altitude of the pyramid, of length h, is the line segment from vertex K perpendicular to the plane of the base. Definition: a regular pyramid is a pyramid whose base is a regular polygon and whose lateral edges are all congruent. Suppose that the pyramid in Figure 9.15 is a regular pentagonal pyramid. Then the lateral faces are necessarily congruent to each other. By side, 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 triangle KLM is congruent to triangle KMN, is congruent to triangle KNP, is congruent to triangle KPQ, is congruent to triangle KQL. Each lateral face is an isosceles triangle. In a regular pyramid, the altitude joins the vertex of the pyramid to the center of the regular polygon that is the base of the pyramid. The length of the altitude is height h. Definition: the slant height of a regular pyramid is the altitude from the vertex of the pyramid to the base of any of the congruent lateral faces of the regular pyramid. In our formulas and explanations, we use script letter L to represent the length of the slant height of a regular pyramid. See Figure 9.16c. For a regular square pyramid with height 4 inches and base edges of length 6 inches each, find the length of the slant height, L. See Figure 9.16. Solution: in Figure 9.16, it can be shown that the apothem to any side has length 3 inches, 1/2 the length of the side of the square base. Also, the slant height is the hypotenuse of a right triangle with legs equal to the lengths of the altitude and the apothem. By the Pythagorean theorem, we have L squared equals A squared plus H squared. L squared equals 3 squared plus 4 squared. L squared equals 9 plus 16. L squared equals 25. L equals 5 inches. Theorem 9.2.1. In a regular pyramid, the length A of the apothem of the base, the altitude h, and the slant height L satisfy the Pythagorean theorem. That is, L squared equals A squared plus H squared in every regular pyramid. To lay the groundwork for the next theorem, we justify the result by taking apart one of the regular pyramids and laying it out flat. Although we use a regular hexagonal pyramid for this purpose, the argument is similar if the base is any regular polygon. When the lateral faces of the regular pyramid are folded down into the plane, as shown in Figure 9.17, the shaded lateral area is the sum of the areas of the triangular lateral faces. Using area equals 1/2 BH, we find that the area of each triangular face is 1/2 S times L. Each side of the base of the pyramid has length S, and the slant height has length L. The combined areas of the triangles give the lateral area. Because there are n triangles, capital L equals n times 1/2 times S times L equals 1/2 times L times the product n times S. Capital L equals 1/2 L times capital P, where P is the perimeter of the base. Theorem 9.2.2. The lateral area, capital L, of a regular pyramid with slant height of length script L and perimeter, capital P, of the base is given by capital L equals 1/2 L times capital P. Find the lateral area of a regular pentagonal pyramid if the sides of the base measure 8 centimeters and the lateral edges measure 10 centimeters each. See Figure 9.18a. For the triangular lateral face, see Figure 9.18b, the slant height bisects the base edge as indicated. Applying the Pythagorean theorem, we have 4 squared plus L squared equals 10 squared. So 16 plus L squared equals 100. Now solve for L. L squared equals 84. L equals the square root of 84. L equals the square root of the product 4 times 21. L equals the square root of 4 times the square root of 21. L equals 2 times the square root of 21 centimeters. Now, capital L equals 1/2 L times capital P becomes capital L equals 1/2 times 2 times square root of 21 centimeters times 5 times 8 centimeters. Capital L equals 40 square roots of 21 centimeters squared, which is approximately equal to 183.30 centimeters squared. It may be easier to find the lateral area of a regular pyramid without using the formula of Theorem 9.2.2. Simply find the area of one lateral face and multiply by the number of faces. In example 2, the area of each triangular face is 1/2 times 8 times 2 square roots of 21, or 8 square root of 21. Thus, the lateral area of the regular pentagonal pyramid is 5 times 8 square roots of 21, which equals 40 square roots of 21 centimeters squared. Theorem 9.2.3. The total area, surface area, capital T, of a pyramid with lateral area, capital L, and base area, capital B, is given by capital T equals capital L plus capital B. The formula for the total area, capital T, of the pyramid can be written capital T equals 1/2 L, capital P, plus B. The pyramid in Figure 9.20a is a regular square pyramid rather than just a square pyramid. It has congruent lateral edges and congruent faces. The pyramid shown in Figure 9.20b is oblique. It has neither congruent lateral edges nor congruent faces. The factor 1/3 in the formula for the volume of a pyramid provides exact results. This formula can be applied to any pyramid, even one that is not regular. In Figure 9.20b, the length of the altitude is the perpendicular distance from the vertex to the plane of the square base. Theorem 9.2.4. The volume, capital V, of a pyramid having a base area, capital B, and an altitude of length h is given by capital V equals 1/3 capital BH. Find the volume of the regular square pyramid with height h equals 4 inches and base edges of length s equals 6 inches. Solution. The area of the square base is capital B equals 6 inches squared, or 36 inches squared. Because h equals 4 inches, the formula capital V equals 1/3 capital BH becomes capital V equals 1/3 36 inches squared times 4 inches. Capital V equals 48 inches cubed. To find the volume of a pyramid, we use the formula capital V equals 1/3 capital BH. In many applications, it is necessary to determine capital B or H from other information that has been provided. Table 9.1 reminds us of the types of units necessary in different types of measure. Table 9.1. Type of measure, geometric measure, type of unit. Linear, length of a segment, such as length of slant height, inches, centimeters, etc. Area, amount of plane region enclosed, such as area of lateral face, inches squared, centimeters squared, etc. Volume, amount of space enclosed, such as volume of a pyramid, inches cubed, centimeters cubed, etc. Theorem 9.2.5. In a regular pyramid, the lengths of altitude h, radius r of the base, and lateral edge e satisfy the Pythagorean theorem. That is, e squared equals h squared plus r squared. Plane and solid figures may have line symmetry and point symmetry. However, solid figures may also have plane symmetry. To have this type of symmetry, a plane can be drawn for which each point of the space figure has a corresponding point on the opposite side of the plane at the same distance. Each solid in Figure 9.24 has more than one plane of symmetry. In Figure 9.24a, the plane of symmetry shown is determined by the midpoints of the indicated edges of the box. In Figure 9.24b, the plane determined by the vertex and the midpoints of the opposite sides of the square base leads to plane symmetry for the pyramid.